Hello, everyone. Today I'm going to work from the Module 9 homework. I'll start with Section 4.1, problem number 9. And in this problem, we're asked to find all the critical points and then use the first derivative test to determine the local minimum and maximum. And so first we'll start by finding all the critical points. So the critical points happen when the first derivative is equal to 0. And remember, our local mins or maxes in our original function are also going to occur when the first derivative is equal to 0, because the first derivative is the slope of the line, the slope of the tangent line to the curve at that point. And when we're at a turning point, a max or a min, the slope of that line is 0. Now, we can have first derivative equal to 0 and not have a turning point. And that's why we have to check to make sure that those critical points are actually turning points. So let's go ahead and do this. So the first thing we're going to do is find the first derivative. And when we do that, we use our power rule here, 12x cubed minus, use the power rule here, 12x squared, and then the derivative of the constant 6 is just 0, so that's done. I can factor this and give me 12x squared multiplied by x minus 1 when I factor that out. And the reason I want to factor it is because, remember, I'm trying to find the critical points. So I'm going to set the first derivative here equal to 0. And now that this is in its factored form like this, I can say, okay, this is going to happen, all of this derivative will be equal to 0 when either the first term is equal to 0, and it would also happen if the second term was equal to 0. So in other words, 12x squared equals 0, and that would also happen when x minus 1 equals 0. So in this case, we have x equals 0 because x squared equals 0, which means x equals 0. And in this case, we have x equaling 1. And so there are our two critical points at x equals 0 and x equals 1. Now it asks us to use the first derivative test to determine whether these are local mins or local maxes. And so the first derivative test tells us, hey, you know what, sketch out a little number line here and put your critical points on that number line, 0, 1, and now see what's going on with the derivative in the intervals before and after each of those critical points. So like in other words, when x is some value less than 0. So we can even plug in like -1. Okay, let's plug in -1 into our derivative. And when we do that, we would see that f prime at -1 is going to give us 12 times 1 times -1 minus 1. And this is a positive, and this is a negative. Positive times negative is going to give me a negative. Notice I don't even really care what the actual value is. I'm just looking to see, is my derivative positive or negative? Because I know that if my derivative is negative, that means that the original function is decreasing in that interval. Okay. Now let's see for some value between 0 and 1. So I'll try a half. Okay, so f prime at a half. This would give me 12 times a half. Oh, well, it'd be a half squared, which would be a fourth. And then this would give me 1/2 minus 1. Again, this is all positive. This is negative. Positive times negative is a negative. So again, my first derivative is negative in this region, meaning that my original function is still decreasing. So I can see here that the critical point x equals 0 is not a minimum or a maximum, because to the left of x equals 0, my function is decreasing. To the right of x equals 0, my function is decreasing. So I just have a decreasing function through that whole region. So now I have to check at the next critical point, which is x equals 1. So go to the right side of that, and I can try 2. Okay, so f prime at 2 is 12 times 2 squared, which is 4, times 4 minus 1. In this case, again, this is all positive. 4 minus 1 is positive. Positive times positive is a positive, which means now in this region, my graph is increasing. Everything to the right of x equals 1, the graph is increasing. So since I have a negative first derivative on the left and a positive first derivative on the right, that means my function is decreasing to the left of 1 and then increasing to the right of 1, which means that I have a local min at x equal 1. All right, so that is my local minimum that I was able to find using the first derivative test. It doesn't ask us to, but I also want to show how you can find that that would be a local minimum using the second derivative test. So if I use the second derivative test, I see that f double prime of x would be, and I'm going to go back to this equation up here to take the derivative, because that's a lot easier to take the derivative of two separate terms. So again, I use the power rule. I would get 36x squared minus 24x. Okay, and so that's my second derivative. And now I know that if my second derivative is positive, so if the second derivative is positive, then my original function is concave up. Likewise, if the second derivative is negative, then the original function is concave down. Okay, so I can take these critical points and see what happens at that critical point with the second derivative. So in other words, the second derivative at 0 is equal to 0 minus 0, which is just 0. Okay, notice 0 is not positive, 0 is not negative, so I'm not concave. My original function would not be concave up, my original function would not be concave down. So this x equals 0 is not a max or a min. All right, let's try the other critical point. The second derivative at 1 would be 36 minus 24, which is 12. That 12 is positive. So that means my original function is the concave up shape. And since it's concave up, that means that I have a local min at x equals